So, my name is Samir and I'm part of the product management team here at MapleSoft. My particular job is to speak to our customers and help them to better understand our tools, technologies and services. This webinar is about why Maple fundamentally provides a compelling environment for signal processing. You may be coming from a different tool, in which case I hope to talk about some of the more unique Maple features. So without further ado, just to place the rest of this webinar into context, I'd like to show you two Maple applications in signal processing. So let me just tab into Maple. And these two applications I've just picked at random. So I'm not going to go into this in too much detail. I just want to talk about some of the more general concepts involved. In this application, we're looking at coded excitation signal analysis. So at the top we have a description and a diagram of the problem domain, and then below that I have some equations and Maple commands. Here I've obviously got a symbolic integral. I have some plots which represent some aspect of my application. There are also animations in this document, so if I just click here I can play this animation. What I'd like to emphasize is that I've annotated this worksheet with text as well, so you can read this document, you can understand it, you can understand what all of the commands mean. So this is just one particular look for a Maple worksheet. You can also create a Maple application that looks like this. Here I don't see any commands, I don't see any equations. They're there, but they're under the hood. What I can do is click a button, let's load a wave file, and let's plot a spectrogram. And there we go. So I have a spectrogram, I have the power spectrum, and the waveform as well. What I can do with this application is filter the audio file. So let's specify an IIR filter and let's place the critical cutoff frequency at this point. What I can do now is replot the spectrogram, and you can see that some of the high frequencies are now attenuated here. So let's jump back into the presentation. I want to show you the type of work that we're getting involved in here as a company. In our consultancy group, we build system-level models and then analyze those models using Maple. Recently, we built a systems-level model of a piezoelectric stepper motor using high-level electrical and mechanical components. We did that in our tool MapleSim. We can then simulate the model to get a time-based simulation. Now, typically piezoelectric motors are associated with frequencies in the ultrasonic range, maybe 100 to 200 kilohertz. Let's say that we want to isolate the frequency of this particular motor. You can easily extract a description of the model into Maple and plot the power spectrum and spectrogram. As a part of this webinar, we prepared a signal processing technical resource pack. It's a library of Maple worksheets and applications that explore and implement various signal processing concepts. If you'd like us to send you an electronic archive, please contact support@maplesoft.com after this webinar. In this technical resource pack, we have applications that cover signal denoising with FFTs and wavelets, frequency domain systems identification, an application that plots spectrograms and power spectrums of various audio files. This is a rather fascinating application. Here we compress brain MRI images with wavelets. There's also a more basic introduction into wavelets. There's an application that downloads sunspot periodicity data from the internet and analyzes that time-based data to identify the period of sunspots. There's an application for tune mask damper design. This is a rather unusual application of FFTs. Here we're actually pricing European options, financial derivatives with FFTs. There's an application that analyzes blood pressure data with wavelets. And of course there's the application I've just shown you for coded excitation signal analysis. And as I said, if you want this application resource pack, please contact support@maplesoft.com after the webinar. We'll be more than happy to send you an archive of the application. So in terms of signal processing functionality in Maple, you can generate signals, you can visualize results through a range of plotting tools, including power spectrums, spectrograms, and also more basic plots. You can calculate signal statistics, you can convert signals from one sample rate to another, you can perform FFTs, wavelet analysis, and there are various classes of wavelets. There are tools for numeric and symbolic convolution and correlation. There are various windowing functions. You can design FIR and IIR filters and more. Signal processing itself is a fairly broad term, and this has many nuances. For example, signal processing means different things to data scientists, electrical engineers, mechanical engineers, or biomedical engineers. A biomedical engineer may want to smooth blood pressure and pulse data with a wavelet. An automotive engineer may want to analyse a spectrogram of engine sounds to identify characteristic frequencies or determine shift points, and an electrical engineer may want to do something completely different. For example, they may want to model ultrasound transmission through a bandgap medium. So in the space of a short webinar, it's difficult to cover all the bases. So rather than focus on the minutiae of signal processing in one discipline, I'd like to provide a broader overview of why you'd want to use Maple for implementing and exploring these concepts. So we'll talk as much about Maple in general as we will do about signal processing. So Maple's traditionally been known as a computer algebra tool, and that's a fundamental part of its heritage that we're very proud of. And many engineers have used Maple at university in their calculus courses to solve differential equations and integrals. There's also a significant amount of numeric computation features in Maple as well, one part of which is signal processing. So why would you want to use Maple instead of other more traditional tools for signal processing? And by traditional, I mean command line oriented tools like MATLAB, as well as high level programming languages like Python. I've also known engineers use Excel for signal processing, and frankly, that's a really bad tool for this application. Many signal processing tools are essentially coding environments. The commands, the code, are essentially programs, and if you want to document the code, you either have to do it separately in a word processing tool or write inline code comments. And plots are given in a separate window, they're not inline to the code. In short, there's very little feedback between the context of the application, the commands, and the actual results. Frankly, a continuous smooth flow of feedback is critical to increase productivity, especially if you're developing new algorithms, exploring the solution space, or just exploring concepts at the educational level. There's also fundamental questions about the maintainability of programs written in this more traditional style. It's difficult to pass them on to other people or to work in a team, because it's certainly more difficult to get a sense of the conceptual flow of the program. A Maple document, however, is a much richer environment. You can include equations in natural math notation, explanatory, fully formatted text, just like a word processing environment. You can also copy and paste in pictures from other tools and other elements as well. In essence, this means you can capture the assumptions, background information, as well as the calculations. I'd also like to highlight the quality of Maple's visualizations. You can produce some very visually impactful plots and charts. You can finesse the look and feel of these plots right down to the precise colour grading of the colour range on a spectrogram. And the plots and visualizations are inline in the worksheet. That gives you a close connection between the algorithm or the code you're developing and its visual representation, the results. Maple also talks to other tools and data sources. At its simplest level, you can simply import data from an Excel spreadsheet or a text file, but at a deeper level you can communicate with, for example, MATLAB. If you have MATLAB and Maple on your laptop, you can exchange equations and functions between the two interactively. Maple also talks to CAD packages like NX, Autodesk and SolidWorks. This means you can develop a parameterized CAD model, extract its design parameters and constraints into Maple, perform some kind of design optimization, and then push those optimized parameters back out into the CAD model. Maple will also communicate with the internet, with networked data sources. This command, for example, connects to a source of live sunspot numbers on the internet and imports that information straight into Maple. Once you've developed your Maple application, you can deploy it free of charge via the Maple Player. I think if you Google the Maple Player, it'll be the first or the second link. This is essentially a free runtime version of Maple. The concept is that you use your main license of Maple to create applications. You add in interactivity with dials, gauges, widgets, radio buttons, checkboxes and more, and then you can deploy it free of charge using the Maple Player. All of these tools are supported by a range of other functionality for optimization, control systems, analysis, matrix computation and more. As you probably already appreciate, Maple can also do symbolic math that I'll show you in a few minutes, code generation and systems modeling. So for example, you could solve a differential equation analytically, get a long complicated result and then convert that result into C code. Maple's also a very efficient environment for signal processing. We've had signal processing functionality in Maple for some time, but that code was getting dated and didn't make use of certain modern CPU-specific optimizations. So we introduced a new set of tools based upon third-party technology that's faster and more memory efficient. Here's a benchmark. So let's say that we're calculating the FFT of a large data set. In this case, it's 2 to the power 26 data points. That's about 67 million, I think. Maple's older FFT function would take maybe 13 or 14 seconds. Maple's newer FFT function, introduced I think a couple of versions ago, takes a quarter of that time, 3 or 4 seconds. And we're making performance gains like that throughout the Maple system. So what I'd like to do now is jump into a deeper demo of some signal processing functionality within Maple. So let me just open a worksheet that I'm going to work from. So Maple's a very strong symbolic math tool. And there are certain symbolic signal processing concepts, such as convolution, that can be explored symbolically. And this is just an example. Here, I've defined a piecewise function. That's a square wave. So let's plot this function so you can see what it looks like. So, as you can see, it's simply a square wave. So let's do the symbolic convolution of this square wave with itself. And this will use Maple's int function. This function actually calculates integrals symbolically, analytically. And this is just the standard definition of a convolution. And x goes between minus infinity and plus infinity. So if I hit enter now, Maple calculates the symbolic convolution. Let's assign the result of this to a Maple variable. And let's plot the result. And if we've done this correctly, I think we should get a triangle wave. And there we go. So this was a pretty simple symbolic analysis. You could probably do this very easily by hand. But one of the benefits of using a tool like Maple is that you can do so much more. This is a far more complex example of symbolic convolution. Here we're calculating the convolution of a cosine under a hand function with a cosine under a wider hand function. So if I hit enter at this point, this takes a few seconds for Maple to calculate because it is such a complex function. But here we go, this is a much larger symbolic result. It's many pages long. But Maple does this quickly and efficiently. So, Maple has an ecosystem of technical analysis tools. One of those tools is code generation. So you can actually translate this large symbolic expression to, say, C syntax, Java syntax, Visual Basic, Fortran, Perl, or Python. So let's say that we wanted to convert this into C code. I'd use functionality from the code generation package. Let me just record what I assigned this result to. It's assigned to a variable sig. So if I hit enter now, Maple analyzes this code and just converts it into C syntax. There are various ways that you can actually fine-tune and tweak the generated C code. For example, I could ask Maple to optimize the C code so common sub-expressions are extracted, evaluated once, but the result used many times. So this resulting C code is far more efficient. Let's try something else. And this I'll do from a new Maple worksheet. So this is a new Maple worksheet. I'm actually going to save it as a workbook. A workbook is a new file container format. In a single workbook you can store multiple Maple worksheets as well as data files such as Excel spreadsheets, text files, images, audio files, and much more. The focus of this workbook is the navigator palette here. This lists all of the individual items that you have stored in your workbook. So if I want to add a data file to this workbook, all I need to do is right click at this point, select attach file, and I think I have an audio file somewhere. Let's pick this audio file. It's a WAV file. So now these two items, the Maple worksheet and the audio file, are stored in the same file on my computer. That means that if I do my Maple analysis, I can actually distribute this project to another person just by sending them a single file. So let's read this audio file into this Maple worksheet. And I'll do that with tools from the audio tools package. If I right click on this audio file, I can copy its path and paste it into this command. If I hit enter now, that audio file is imported as an array. Let's do some analysis on this audio file. I'm going to load up the signal processing package, and these are all of the commands within the signal processing package. So there are windowing functions, tools for FFTs and wavelets. There are tools for calculating the power spectrum, and there are tools for plotting this waveform, let's plot the spectrogram. So if I simply want the spectrogram of this data file, all I have to do is this. So there we go. The spectrogram shows me how the frequency of this audio file varies over time. I actually imported an audio file of a violin note being played under vibrato. So you can see that there are a number of characteristic frequencies. What I can do is tweak the spectrogram, say change the size of the FFT window, apply a windowing function. If I hit enter now, I get a somewhat different plot. I can also ask Maple to include the power spectrum as well. So now I get the spectrogram and the power spectrum. So you can see that the peak frequencies here much more clearly. Let's try filtering this audio file and see how the spectrogram and the power spectrum changes. I'm going to record the sample rate of the audio file into a Maple variable. So the sample rate is 44.1 kilohertz, and I think I'll generate a Butterworth filter with a critical cutoff frequency of, let's say, 10,000 hertz, 10 kilohertz. So let's apply the filter. What I'll need to do first is generate the filter taps. And it'll be a low pass filter. So this is now my array of filter taps, and let's just apply this filter to our audio file, and then we'll update the power spectrum and the spectrogram, and we'll see what the updated plot looks like. So that's my filtered audio, and let's plot the spectrogram and the power spectrum again. And if I've done everything correctly, you should see some changes. So the higher frequencies have been smeared. Let's see what the power spectrum looks like. And there we go. You can see that after about 10 kilohertz, the power of the signal gets attenuated. What I can do if I wanted to is experiment with the cutoff frequency, change that to 5 kilohertz. I could convert this into a high pass filter. And you can see that the spectrogram and the power spectrum reflect those changes. So that was everything I wanted to show you today. I hope I've given you some sense of how Maple can be used for signal processing. There's a lot more to Maple. It really is a broad, deep, flexible tool. And if you have any further questions, please do feel free to talk to us, either email us or give us a call. And as I said earlier, if you'd like the signal processing technical evaluation pack, please send an email to support@maplesoft.com. We'll be more than happy to send you an archive of the application. It'll be in the workbook file format, so it'll be a single file delivered to you